We experience forces such as weight or normal force. The fact that you can sit down comfortably watching this lecture video instead of floating around in space or sinking down to the floor is because of constant downward gravitational attraction from Earth and upward normal force from the chair acting on you. But have you experienced centripetal force acting on you before? Think about it for a moment. Imagine you are on the annual shuttle bus making a turn at the Yusof Ishak building roundabout. You are undergoing circular motion, which means there must be centripetal force acting on you toward the center of the roundabout. But do you feel a force pulling you toward the center of the roundabout? Really? Because I do not when I'm boarding the bus. Quite on the contrary, in fact, I actually feel as if I were being tossed in the radially outward direction. The effect is even more significant, coupled with some profanities when the uncle bus driver is speeding up as he's making the turn. Now there are two things I would like to bring up through this illustration. First, to emphasize what we learned in the last video. Centripetal force is not to be included in the drawing of free body diagram. If you are to draw the free body diagram of yourself on the bus, you can draw forces such as weight, normal, and friction force with the bus floor, etc. because these are physical force acting on you. But you should not draw the centripetal force on you. Or to be more exact with my words, you should not draw mv squared over r on you. In the same sense, you should not draw m times a on yourself. A or phi is a kinematical quantity. How can a kinematical quantity act on an object? It makes sense to say I'm applying a force on such and such, but it makes no sense to say I'm applying acceleration to such and such. Say for example, you are falling. Weight is acting on you and therefore you are falling down. So you draw weight on your free body diagram, but not m times a. If you are then asked to compute your acceleration, you equate weight to m times a, and from there you can compute that you are accelerating down at gravitational acceleration as expected. In conclusion, you draw weight because weight is acting on you, but m times a does not act on you, and hence you should not draw m times a. You draw weight, friction, normal force as the bus is turning because those forces are acting on you. But mv squared over r does not act on you, and hence you should not draw it either. Do you see the parallel between the two? But what about tossing and swirling inside the bus? What force or forces that toss your body into the air? Well, it turns out that it is not force that tosses your body inside the bus. It is your own mass that caused the phenomenon. Remember what I said about mass in the beginning of Lecture 5 series? Mass is the measure of inertia. It is the measure of how easy or difficult it is for an object to change its state of motion. Now you put this concept side by side with your last experience riding on any shuttle bus in your mental picture. Can you recall that your body was being tossed around when the bus is braking or accelerating? When the bus is moving steadily, it is a comfortable ride, isn't it? Also, can you recall the direction when your body was tossed? Isn't it always opposite to the direction of the bus acceleration? When it was speeding up or accelerating forward, you were tossed backward. Or when it was braking or accelerating backward, you were tossed forward. So what can we conclude from this experience? When the bus is speeding up, the bus is accelerating, but your body, because of inertia, is not going to immediately speed out along with the bus. This sort of being left behind results in the impression as if you were being tossed to the back of the bus. Similarly, when the bus suddenly brakes, your body is still in the state of moving steadily with the bus. This results in your body moving faster than the bus, and you are tossed forward. The more massive you are, the larger the inertia, and the more pronounced the effect is, as you might have experienced or seen for yourself. When the shuttle bus keeps on jerking, the big-sized people on board the bus would find themselves very difficult to balance. The same principle is applicable when the bus is turning. I will use this bug as an illustration. The bus or the bug is accelerating toward the center of the roundabout as depicted by the red arrow. But because of your inertial mass, your body inside the bus tends to follow a straight line motion as depicted by the green arrow. This results in your body being impressed against the further side of the bus from the center of the roundabout. In other words, you are tossed in the radial outward direction. We have technical jargon to describe this fictitious force which tosses you in the radial outward direction when the bus is turning. It is called centrifugal force. The bottom line is this. You experience this apparent or fictitious force because you are inside a bus which is accelerating. If you choose a coordinate system to be a point inside the bus, then you are actually inside an accelerating frame of reference. For somebody who is standing outside the bus, for example somebody who is waiting at YIA's bus stop, observing the whole episode of you being tossed around inside the bus, he or she will not see that as a result of any forces acting on you. From his or her point of view, your body or your inertial mass is simply playing catch-up with the bus. This idea of fictitious force in accelerating frame of reference. Now, I use the term coordinate system and frame of reference interchangeably. Both refer to some kind of reference system where vector quantities makes physical sense, like 2 meters from where, or 5 meters per second with respect to who. So yeah, this idea of fictitious force in accelerating frame of reference brings us to this whole idea about inertial versus non-inertial frame of reference. To tell you the truth, the definition of inertial and non-inertial frame of reference are not as clear-cut as what I presented here. You ask any theoretical physicist and the discussion will never come to an end. But I do not want to unnecessarily complicate matters at this point. As far as this course is concerned, it is sufficient for you guys to keep this in mind. An inertial frame of reference is a constant moving frame of reference, while a non-inertial frame of reference is an accelerating frame of reference. When the bus is moving steadily, you are inside an inertial frame of reference. When the bus is speeding up, you are inside a non-inertial frame of reference. When you are inside a non-inertial frame of reference, you will experience those sort of spooky fictitious force which physically are non-existent. If you're critical, immediately you will identify these two issues. First, isn't whether something is moving at constant velocity or not relative to another frame of reference. If you're on board the bus, you know the bus is moving at constant velocity because you are observing that the lamppost outside is moving at constant velocity. Of course, in actuality, the post is not moving, but not moving is a special case of constant velocity. That is constant zero velocity. The post is therefore a valid inertial frame of reference. But then again, one may argue, in which reference the post is constantly at zero velocity. Certainly not to you inside the bus, because you do see the post moving from inside the bus. But the post is at zero velocity if it is taken with respect to a nearby pedestrian who happened to be sitting down at the bus stop. The discussion goes on, but in essence, for a particular frame of reference to be called inertial or not, it has to be defined with respect to another inertial frame of reference. Are you confused? If you are, do replay what I just said. For a particular frame of reference to be called inertial or not, it has to be defined with respect to another inertial frame of reference. Now you ask me, does that mean you need an inertial frame of reference to define another inertial frame of reference? Well, as confusing as it may sound, the answer is yes. You do need an inertial frame of reference to define another inertial frame of reference. It does sound like a catch-22 sort of argument. The question is then, is there any such thing called universal inertial frame of reference which does not need to refer to another inertial frame of reference? Well, I will not provide the answer here. This is one of the reasons why if you ask any theoretical physicist about it, as I mentioned earlier, very likely you will not receive a nice concise answer. At the end of the day, as far as taking any shuttle bus is concerned, you do know whether you are inside a steady moving bus or an accelerating one, do you? Second, I said in Lecture 3, when we were discussing coordinate system, the law of physics is the same in any system of frame of reference. Now with this our new knowledge about inertial and non-inertial frame of reference, I would like to rectify what I said earlier to be, the law of physics is the same only in any inertial frame of reference. That's because in a non-inertial frame of reference, fictitious forces take effect. Imagine you are conducting an experiment on the ground, on board a steady moving bus and an accelerating bus. Obviously, the fictitious force will affect your experiment, and your result will not be consistent with the result you will get from conducting the experiment on the ground or on board the steady moving bus. The result from the latter two will be consistent. So it is always a bad thing to be inside a non-inertial frame of reference? Well, yes it is when you are on board of a jam-packed shuttle bus that keeps on jogging forward and the air conditioner is not working. But are you aware that you can also artificially create gravity inside an accelerating frame? Let's invite our boy from Lecture 3 back. This time, our boy is on board of a rocket going on an interstellar mission. As you would imagine, being far away from Earth or any nearby massive planet, our boy is practically weightless. Newton's first law then said that in the absence of force, any object will continue to maintain its current state of motion. If the rocket happens to stop, it will stay motionless. If it is already moving to begin with, it will continue to move at constant velocity. What will happen when the rocket starts accelerating at 9.81 meters per second square? Well, just like what happened to you inside the shuttle bus, our boy will experience being hurled toward the back of the rocket at the acceleration 9.81 meters per second square. While from the point of view of somebody outside the rocket, it is actually the back of the rocket that is pressing against our boy's mass, who simply refused to bust along at 9.81 meters per second square. The interesting thing is this: if our boy has no awareness at all that he is on board an accelerating rocket, for instance, like what happened in those movies where our boy is kidnapped from Earth and prisoned inside a windowless compartment, unable to see outside to look for reference, our boy would think that he's still on Earth. There is no way he will be able to distinguish whether he's on Earth or on board the rocket. As a matter of fact, there would not be any single physics experiment our boy could conduct which could help him distinguish the two conditions. He is experiencing exactly the same 9.81 meters per second square gravitational acceleration as if he were on Earth, provided that the rocket continues to move at constant acceleration of 9.81 meters per second square, of course. If the rocket stops or stays at constant velocity, our boy's inertial mass will finally catch up with this constant velocity and is no longer pressed against the back of the rocket. Our boy will be weightless again. Well, let me be honest with you. I wasn't the one who came up with this thought experiment. It was Einstein. Through this thought experiment, Einstein realized that one is actually able to simulate the effect of gravitational force or gravitational acceleration by putting himself inside an accelerating frame of reference. Physicists refer to this as the equivalence principles. This realization is the first step toward Einstein's theory of general relativity, which is not the scope of this course, so I will not go any further into this discussion.